In 1.7, we're going to learn how to find the average rate of change of a function, which is kind of like the slope of a function. So we'll do a little slope between 2 points. So if we know how to do slope, we should know how to do average rate of change over an interval. And then we're going to do a lot of stuff with the graph of a function. We're going to determine where it's increasing, decreasing, or constant. And then as we figure those out, we'll be able to identify local maxima and minima. And then we'll also be able to tell which ones are the absolute maximum and absolute minimum. And then we'll determine concavity. All of these are going to be from the graph. So from a graph. All right, so the introduction here is showing gas prices over the last several decades. We have it going from 2005 all the way to 2012. Sorry, it's just showing 2005 to 2012. And we can consider this as the gasoline price as a function of the year. Determine the change in gas prices between 2005 and 2008. That's one question. 2009 and 2012, that's another question. And then 2005 and 2012, that's another question. So this is a three-part question. And when it says to determine the change in gas prices, that's asking for the average rate of change, which is going to be the slope between those 2 points. So on the first part here, 2005 and 2008, we're figuring out what happened to the change in gas price. Oh, it's just asking for the... Sorry, this one is just asking for the change in gas price. So what was the price in 2008? What was the price in 2005? We just want to find the difference of those. So 2005 to 2008. Our change in gas price is going to be the 2008 price, which is the $30.06, minus the 231, which was the price in 2005. So we find this difference here. This is going to be 0.75, which is a 75-cent price change. So you'll need to do 2009 to 2012 and 2005 to 2012 as well. All right, so this is just change in gas price, which is just how much did it go up. In the next part, we're getting into finding average rate of change. So determine the change in gas price between 2005. So we did this. We're going to divide that by the change in the number of years for each interval. This tells us how much gas price changed on average per year. So this is going to be an average rate of change calculation. We're going to take that answer from the first question. Let's call that part A, part B, and part C so we can refer to it. So part A for this this example down here, we'll use that answer from the first part, so 0.75. And we'll divide that by how many years it's taken to get to that kind of increase. So in 2005 2008, the gas price increased by 75 cents. So we're going to find the difference between the years in the denominator, 2008 minus 2005. So we get 0.75 over the course of 3 years, which means we have a 0.25 dollar per year increase. right? That's the this is the average rate of change, or 0.25 is the average rate of change between 2005 and 2008. So you'll need to do that for the other two as well to figure out the average rate of change for those. So in general, is everyone good with that one? I can stay here for a sec. Okay. In general, if we're doing, so let's talk about if we just did 2005, 2006 or 2006, 2007, if we looked at 1 year difference, that's called rate of change because it's just describing how the quantity output changes relative to one increase in the input. So we're going to do average rate of change over longer periods of time or longer periods of the input values. So we're going to say average rate of change is the change in output over the change in input. And you've seen this before. This is kind of like the slope formula that we use to find slope between 2 points. So we're going to call that average rate of change. This has more to do with real world problems. We don't call it slope when it comes to real world problems. Instead, we're going to call it average rate of change. Some stuff about delta, average rate of change of a function. Again, we're given a slope formula. Just instead of y2, y1, we're using function values here, f of b and f of a. We're working on an interval here from a to b. So a lot of questions are going to give you an interval either in that format or they're going to write it in interval notation like that, a to b. And we find the average rate of change using the slope formula from a to b. So let's see if we can do this given a graph. Given the function y equals f of x shown on the graph below, determine the average rate of change on the intervals -4 to -2 and -1 to 2. So we'll call that part A and part B. We'll call this one A and this one part B. I'll do part A, you guys can do part B. We're going to do change in y. So we use delta as to mean change in. So that's the difference between the y's and the difference between the x's. We're going to do f of -2 minus f of -4. Notice how I did the ending point minus the starting point function values. And then we'll do the same thing down here. We'll do -2 minus a -4. Right, so we do ending point minus the starting point for both the function values and the interval starting and ending point. From the graph, what's f of -2? Good. It looks about 5, right? If we go to -2 and go up to the graph, that's a y value of 5. What about f of -4? So we'll do 5 minus 1. I'm going to call that 0. I'm pretty sure -4 is where it hits 0. It kind of looks like it could be at 1, but I think that's 0. And then in the denominator we have we can change this into a -2 plus 4 because we have the minus negative. This will be 5 divided by 2, and that's as simple as that's going to get, right? That's going to be our average rate of change on the interval -4 to -2. Essentially what's happening here is we're taking these 2 points, -4 comma 0 and 5, or sorry, -2 comma 5, and we're just finding the slope of this line. Does anyone know what this line is called? Just randomly. if you draw a line between 2 points on a curve. Anyone know the name of that one? No, that's okay. I didn't expect you to know that one. But this is called a secant line. Just in case your other math teacher asks you what that line is called, you can be the one to tell them. So we're basically finding the slope of that line, which is giving us an average rate for the blue curve, right? So the slope of this line is an average. The slope of that line is the average slope for the blue curve. So you see the blue curve kind of increasing up to a certain point, and then it's like flat up here, right, for a second, and then it goes down a little bit. So all of those individual points, like all of these slopes added together and then divided and then found an average, is giving us the slope of this secant line, right? So it's an average slope over that interval. All right. Any questions so far? Okay. What are we doing next? That's all we have for average rate of change. Next, we're going to look at some graphs and determine where the graph is increasing, decreasing, constant, and then we'll talk about maximums and minimums and inflection points and concavity. So as far as increasing, decreasing goes, we read left to right, so we're going to follow these graphs left to right. This number line, the x-axis, increases from left to right, so we're going to start with the negative most and work our way towards the positive x-axis and continue on with increasing numbers. So if we're reading left to right, if we're a point moving along this blue curve, then from left to right, this point is moving up, right, all the way up to this peak point here. There are certain points where it switches from moving up to moving down, and that's where the increasing, decreasing of graphs are determined from. So these peak points. So if a point left to right is moving up on a graph, then that's considered increasing over that interval. If the point would be moving down, like this part in the middle here, that's a part of the graph that's decreasing. And then the point starts moving up again, which we call an increasing interval, right? So if I were to write the intervals of increase and decrease for this graph here, we'll do it on the side here, increasing on, and we'll write the intervals where it's increasing, and then decreasing on, and we'll write some intervals where it's decreasing. There's only one interval where it's decreasing, so I'm going to write that one first. From this red point to this red point, it's decreasing. When we talk about where a graph is decreasing, we're talking about x values. We don't care about how high the function goes or how low the function goes. We're talking about from here to here in this slice. I kind of missed the point there. But in that region, the graph is decreasing, right? The blue line is going down. So we're going to write the interval for that region there, which is -2 to +2. And we use parentheses because it's not increasing nor decreasing at this point here or at this point here. On those peaks and bottommost points, the graph is neither increasing nor decreasing. It's kind of flat there. It's just sitting flat. So we have this. These are x-axis interval, right? Same thing with the increasing. So what are the intervals where this graph is increasing? Well, it's this part over here. It's increasing all the way up into the topmost point, and then over here from the bottommost point to to the right forever, right? So how do we write those two intervals in interval notation? How do we write this first one? Someone tell me what the interval is here for x values. So the interval. Go ahead.
Infinity to 2, right?
Good. So the interval for this is going to be everything to the left of this point, right? It's this. It's this interval to the left of -2. And how we write that in interval notation is -infinity to -2. All right, so that's one interval where it's increasing. And then what we can do is we can just join more intervals to this by just using a union symbol. So we're going to say union. And then the other increasing interval is from this point to the right, which is from here all the way to the right forever, right? So that's going to be from 2 to infinity. So we have an increasing interval. Again, these are x-axis intervals. There's a more formal definition for increasing, decreasing. This is just saying that on an interval from A to B, like from -2 to 2. Well, let's look at the decreasing one. From -2 to 2, we said this graph was decreasing. So if I'm going from -2 to 2, and I pick 2 points, one to the left and one to the right of one another, then I should see a lower y value for the rightwards point and a higher y value for the point to the left, right? So if I choose like -1 to +1, for example, in that interval, then my point at -1 should be higher than my point at positive. Oh, sorry, yeah, higher than the point at +1. That shows that the graph is going down in that interval that you've chosen, right? But visually, you can look at a graph and be able to tell if it's going up or going down, as long as you know how to read from left to right on a graph. Okay, you can do this one, I believe, now that we know how to identify increasing, decreasing. We'll just identify these peaks here. We'll say this is a point, this is a point, and this is a point, right? And then you can use those points to figure out where the graph is increasing and where it's decreasing. Moving on to local maxima and local minima. So we have a nice little picture here. If a graph ever switches from increasing to decreasing, that point, that the highest point or lowest point, is going to be called a local maximum or local minimum, depending on which way your graph turns. Now, why is it called local? You might say maximum kind of makes sense, right? Why don't we just call it a maximum? It's called a local maximum because there are points on the graph that are not the maximum or the minimum of a graph, right? So this point here specifically at 4 comma whatever is a turning point, right? The graph is switching from going down to going up at that point. But it's not the lowest point of the whole blue curve, right? We have lower points over here than this point. So that's why it's called the local minimum in this one's case, because it's going from decreasing to increasing. It's locally a minimum because if you were to zoom into that and you don't see any other points other than the points around it, then it's the minimum of those points, right? If we just look at a window around that point and we're just seeing that, then this looks like a minimum. So in its neighborhood, in the local area, this is the minimum point on that blue curve. Does that kind of make sense if you're only seeing like this part of the graph? if we're only looking at a window around it. Compared to the points around it, it's a minimum. So basically this is a zoomed in window of some bigger graph. And if there's a turning point from increasing to decreasing or decreasing to increasing, then it's called a local maximum or local minimum. Maximum for high points, minimum for low points. The formal definition is essentially saying what I just said in a more mathematical way. This is saying that a function f has a local maximum at a point c comma f of c. We'll just say that's what this point is here. Let's change these letters here so that this makes more sense. We'll call this c and we'll call this b. So the definition makes sense when we're looking at this. And this is going to be f of c, because that's what they're calling the local maximum c f of c, right? So this point here would be c comma f of c. So this is saying, the formal definition is saying that this point here is considered a local maximum on an interval a to b, so in this window here, if f of c is higher than or bigger than f of x for every x that's not c on the interval. So for every one of these points in here, right, there's infinitely many in here, so we can't list them all, but every point other than our point that we're saying is the maximum, this point up here is bigger, or this y value is bigger than any of these other random y values. That's what makes it a local maximum. Okay, so f of c is bigger than f of x. So if I pick another random x here, I get my point f of x for that. This f of c is bigger than f of x. That's all the definition is saying, right? So if it's bigger than all of these points and all of these points in this open interval, then it's a local maximum. It's just we have to be very rigorous and specific when we write definitions. You can learn it as just a high point and a low point, and it'll serve your purpose. Local minimums and local maximums are also called local extrema, just as a joint word. You may see that. The question may say, identify the local extrema. That's asking for both the local maximums and local minimums. Okay? So if you see this wording here, identify local extrema, that means find local max and local mins. Maxes and local mins, if there are more than one. Right, you got to find all of them. Okay, that's enough about maximums and, well, that's enough about local maximums and minimums. Let's talk about absolute maximums and minimums. If local is just looking at a window around a point and saying this is the lowest point, this is the highest point, absolute maximums and minimums are talking about the whole graph. So we're not zooming in on a window. We're saying that a point f of c or c comma f of c is the absolute maximum of a graph if it's bigger than all x's in the domain of f. So looking at the whole graph, this blue curve that goes down forever like this, what is the highest point on this graph? What is the lowest point on this graph? Right? Can anyone identify the highest point on this graph?
Seems to be 7 as the x and then 150 as the y.
Good. This is going to be the absolute maximum. What about the absolute minimum, the lowest point on the graph?
There is no absolute minimum.
Good. Why not?
Because the function extends infinitely to negative infinity.
Yeah, this tip here that has the arrow on it, this is telling me that there is no absolute minimum. Right? And you can write that and explain that the graph extends down to negative infinity on the y-axis, or in the y values, so there is no absolute minimum. But so that's the absolute extrema that we just identified. Well, couldn't identify because there is no absolute minimum, but we can find some local ones, right? So we can find a local high point here and a local low point here, and we can probably estimate what those are. So I'll let you do. I'll let you identify those. Now, when it says find all absolute extrema, that doesn't mean this, right? I'm just showing you where it is. This is not finding it. It's not like, oh, here it is. You have to write down absolute max and write down what it is, the absolute minimum. Forgot the X, or the S. The absolute min, we have to write down what it is, and then a local max and local min. We have to list them in our answer. Are there any questions on absolute maximums and minimums, or relative maximums and minimums, or sorry, local ones?
Do we include the absolute max in the answer for the local max?
Great question. If it is one, then yes. So there's a very specific, there is specific verbiage for local max and local min, right? Is this point a local maximum? Remember what we said about local maximums. Local maximums are in a place where the graph turns from increasing to decreasing. It's not just a high point. It's a high point where there is a window to look at. There is an interval around it that we can compare this point's height to, right? If this point is higher than all points in an open interval around it, which means there has to be a curve on both sides of it, there has to be points on both sides, then it's a local maximum. This point, so this point is, the endpoints can't be local maxes or local mins, okay, because there are no points on the other side of it. If we had points on the other side, if there was like a peak here, then yes, this would be a local and absolute. But in this case, it's not. But to answer your question, in general, yes, you do want to include them if they are actually local maxes and mins.
Okay, thank you.
Mm-hmm. Okay. Any other questions? That was a good question. I was just about to tell you about that. Any other questions? Okay. Last thing we want to talk about is concavity. Whoa. This is not concavity. This is concavity. Interesting. These are not really about concavity. These are all about... I guess there's questions in here about bending up and down. That's about concavity, bending upwards or downwards. So let's talk about what that means on the graph. So this at the top says when the rate of change of a function changes, the graph of the function will bend. So we see some bends here, right? This is a bend, this is a bend. So basically where a graph is turning or curving in a sense. So depending on the direction that it's curved, we're going to determine whether it's a bend upwards or downwards. I really don't like the wording on this, but concavity is essentially going to be the shape of the cup that we're looking at. So if you imagine that these bends, these curves, are in isolated cups, then we're going to identify a U-shaped bend, an upward U-shaped bend, as a concave up, and a downward shaping curve bend as a concave down part of the graph. Right? So we usually don't talk about a single point on the graph when we're talking about concave up and concave down. It's usually an interval. And kind of a weird thing to think about is when the graph changes from being concave up to concave down, or vice versa, right? Because this graph is a smooth curve, right? There's no like sharp turns in it, or like there's no obvious point where it switches in concavity, but there definitely is a part here that's concave down, right? That's a downwards cup. And then there is a cup here that's upwards, right? So there's got to be a point where it switches from being a downwards cup to an upwards cup. We have a down cup here and an up cup here. So somewhere in between, right in the middle, is where that changes. Right? Usually halfway between the high and low points. So if this is going, if the peak here is at -3, and the peak here is at +3, then exactly at 0 is where the concavity of this is going to change. So on the left side of this 0, let me highlight this in red actually, from here, the left side of this graph is where we are concave down. Right? Because it's a downward shaping or a downward shaping cup. And then on the right side of this, it's concave up. Again, I'm not pointing at a specific point here. I'm saying the whole blue curve here from 0 to 6, right? From 0 to 6, this region of the graph is concave up. And then from -infinity, I guess because this goes down forever, from -infinity to 0 is the concave down interval. Hopefully that kind of makes sense. And the switching point is generally at the center point of the high and low points. So you guys can do all of those examples up there. A function is concave up on an interval if the average rate of change increases. That seems kind of weird because, again, we talked about this being concave up, right? On this interval, the average rate of change is increasing on this whole interval. If you look at individual little, like the average rate of change from here to here versus from here to here is going to be smaller. So it is going to increase, even though the graph is decreasing on the left half of it, the average rate of change is going to increase as you move from left to right, right? If you think about slopes, they're negative slopes, but they're getting less and less negative as you go down that slope or go down the curve until you reach a slope of 0 at the bottom here. And then these lines are increasing in slope as you move up and as you move down on the left side. So, I mean, shape-wise, it's easy to tell. Definition-wise, it's a little bit weirder again. So we'll identify some key points here. Where are some high and low points? We have a low point here, a low and a high point here, and a low point here, right? Those aren't necessarily the points where the graph is going to change concavity, but that's going to help us find where the slope or the graph is going to change from going concave up to concave down. So we have a U shape here, we have a concave up region here, a concave down region, and then another concave up region. So you got to identify where those change based on the highs and low points, and then name the concave up and concave down intervals. So I'll name the concave. Actually, no. Do I want to name them on here? I'll actually name them on here. So concave up, go back to the last page, and we'll name the concave down, concave up intervals for this one. So concave down interval, the first one here, is going to be from negative infinity to 0 is concave down. And then it's concave up on 0 to 6. That's where it's concave down, where it's concave up. Again, we're talking about x values here. Whenever we talk about where the function has something, or where it's increasing, where it's decreasing, where it's concave up, where it's concave down, those are all intervals on the x-axis. And then this point here specifically, this point in the middle, has a special name. It's called a point of inflection. At 0, 0, I guess, in this case. But a point of inflection is where the graph changes concavity. So it goes from concave down to concave up, or vice versa. If the graph was concave up first and then it became concave down, that would be a point of inflection as well. So those points of inflection are going to be found halfway between peaks, and then that'll determine where the graph is concave up and concave down. Now, what if the graph were to do something like this, where it's increasing and then it becomes horizontal and then continues back to increasing? What do we think happens here? What is the concavity of this graph? Or what is it, two different concavities? Is there an inflection point? What happens on this type of graph? Let's say our axes are like here or something, right? Let's say the graph looks like that. What happens at, on this graph? About, like, in terms of concavity, because there is no there's not a peak, right? Because the graph never turns down. It just kind of becomes horizontal at a single point here. Let's just say it's this point here. The graph becomes horizontal at this point, and then it continues going upwards. So what can we say about concavity here?
It's constant.
What's constant? Is it concave up the whole time, concave down the whole time? Does it change?
Well, it's constantly increasing. It's not. It doesn't really change. It
Good.
doesn't give you a concave down or concave up.
Well, we do have. Oh, I see. The picture I drew up here. Sorry, I should probably clarify. The picture I drew up here essentially has 4 parts to it, right? So concave up doesn't mean we have to have. It doesn't mean the graph has to turn. That's not what that means. Concave up is any part of this curve is concave up. So if I just look at, if I just zoom in and I look at this window here, and I just see this part of a graph, that's concave up as well. So any segment of a graph that's part of an upwards U shape, so any part of that is considered concave up. So even if I don't have a peak point, even if I look at like half a U, I can't really draw, half a U, that's still considered concave up. Okay, same thing with this one. So maybe we should do like a, I don't know, draw like a line here and say both sides of this half are concave up, right? And then same thing with this one. Both halves of this upside down U are considered concave down. So anywhere on this, if we zoom into a window like this, for example, as long as it has this, it's part of a downwards U-shaped part of a graph, that's considered concave down. Right? So now that we understand that, hopefully, the graph doesn't necessarily have to turn for it to be considered concave up or concave down. So on this graph, this point is going to be significant. Go ahead.
So is it concave down to concave up then?
Yeah, so this part here all the way up until that's part of a downward shape U, right? Or a downward shape like N. Or a downwards cup. So this part here is concave down. While the upwards part after that point is concave up. Right? And then again, this point here is the inflection point. And earlier I said that the inflection point is going to be halfway between the highs and lows, but if there is no high and low and it just switches from concave down to concave up, then it would just be the point where it's like basically horizontal, right? There is no, the graph is neither increasing nor decreasing at that point. It becomes horizontal, and so that point at which it becomes horizontal is going to be the inflection point, where the graph switches from being a downwards U to an upwards U. So this is another thing that can happen, or it could be any part of the graph that they ask about, right? The question could ask about, I don't know, like this window over here, right? If it's asking about this window here, the graph is concave down in that window, in this window here. Anywhere on the red curve, the graph is considered concave down in this one. Oh, I guess I switched my reds and my blues, which is not great, but oh well. Can I change that? I can. Okay. Let's change that. So that my concave ups are blue and my concave downs are red, so I have some consistency in the notes. Cool, cool, cool. Any questions on concavity? And inflection points. All right, so you have some examples to do in 1.7. You also have XYZ homework for all of the sections for chapter 1, right? They're all due the day before the exam, which would be Thursday. And then you also have a chapter 1 review on XYZ that you should be working on. So I'll give you some time here, about half an hour to 45 minutes or so. Do we have 45 minutes? We do have 45 minutes. Let me make some breakout rooms so you guys can work together on these. If you have any questions, feel free to call me to your room, and I can clarify anything you might have questions on. It doesn't have to be for this section. If you want to work on other sections, if you want to work on XYZ homework, that's fine as well. Wednesday, let me stop recording.